Now we're going to start concentrating on a special type of graph called a tree, and then something that's related to a tree, that those are called forests. So first of all, we're going to define what trees and forests are. We're going to show some examples, and then we'll prove one theorem about trees. So let G be a graph. We say that G is a tree if G is both connected and has no cycles. And then a forest is just like a tree, except we don't demand that it's connected. So it has no cycles, but it may or may not be connected. So note from the two definitions that every tree is also a forest, but not every forest is a tree. In particular, if a forest is not connected, it can't be a tree. So here are some examples of some trees. We've seen path graphs, those are trees. Caterpillar graphs, we haven't seen those before, but I'll show you what those look like. You have to use your imagination, but it kind of looks like a caterpillar. The path down the middle is like the spine, and then the little edges and vertices coming off the spine, those are like the little legs on the caterpillar. If we take a caterpillar graph and allow those legs to be of length 2, we get what are called lobster graphs. Also a tree, and again, what makes these trees are, no matter what you do, you can't make a cycle out of that graph. There's no subgraph of these graphs that is a cycle. Now, if you want to look at what a forest looks like that is not a tree, well, it looks exactly like you'd imagine a forest to be. A forest contains trees, a bunch of trees put together. So here's a forest with 3 trees as subgraphs. And again, none of the little trees within that forest has a cycle, but this is not going to be a tree because it's not connected. So let's continue our tree metaphor. So trees, most trees have leaves. So we're going to define what a leaf is. A leaf is a vertex whose degree is 1. So one thing you might have noticed is that every tree and forest has leaves, or at least that we've drawn. And here, let's go back. I'll show you. Right. So if you look on the left one, that one has 4 leaves up in the corners. The path in between has a leaf on the left and a leaf on the right, and the one on the right has 1, 2, 3, 4, 5 leaves. One is the head, if you imagine that as a person. There's a leaf for each arm, and then there's a leaf for each foot down at the bottom. Again, that looks like a person to me. You can use whatever imaginative imagery that you want. All right, so let's go on back. And so it looks like every tree and forest has leaves. And so we're going to prove a theorem to show that that is true. Let T be a tree that has at least 2 vertices. Now, if you just have one vertex, you can get away with not having a leaf because you could just have a single vertex that has degree 0. That's not a leaf. But if you have 2 vertices in a tree, it turns out that T has at least 1 leaf. And so this is going to be a fun proof. We're going to prove this by contradiction, first of all. So we're going to assume that you have a tree that doesn't have any leaves. And then we're going to use an algorithm to prove that some kind of contradiction, right? So we're going to assume by contradiction that we have a tree, but every vertex of the tree has degree at least 2. And then we're going to create an algorithm, and the contradiction that we're going to get from that algorithm is we're going to prove that there's a cycle in there. Of course, since it's a tree, having a cycle is a contradiction. So just recall, we've done a proof by algorithm before, but I want to sort of remind you of the ground rules for a proof by algorithm. So we're going to create an algorithm. We got to do a couple things. Well, 3 things. We've got to, of course, describe carefully what the algorithm does so that everybody understands what the algorithm is. Secondly, we should really justify that whatever step we claim we can do in the algorithm, we actually can do. And then finally, if this is relevant, and a lot of times it is, we've got any conclusions that we make at the end of the step, we got to justify that those conclusions are true. So here are the steps of our algorithm. And they're going to look a little bit familiar because it's actually not too different from the algorithm that we used with Eulerian circuits. Slight differences, but not too different. So we're going to choose a random vertex. There's a surprise, right? And then what we're going to do is note that we have at least 2 vertices, and since it's a tree, it's connected, so there's a walk between those vertices, which means that if we are at a given vertex, in particular the first one, we can move to another vertex along an edge. And what we're going to do is we're going to keep moving along to vertices along another edge until we can't. But the rules are slightly different here. Here the rules are every time we move along an edge to a vertex, it's a vertex we haven't visited before, right? So we're going to start at the first vertex, move to another vertex that we haven't visited, then move to another, and keep going until we can't. So we're going to stop when we are at a vertex that is only adjacent to vertices that we have already visited. All right, so let's see what the output of this algorithm is. So note that every step we make takes us to a vertex we never visited before, right? So the output of this algorithm is going to be a path. So here's our path, v1, v2, all the way to vn minus 1 to vn. And notice that at every single step that we've taken, except for v1 and vn, each of those vertices in the path has two edges coming out of it. So we've used at least two edges. But v1, vn, we've only used one edge. Right? So remember that degree of vn is at least 2, right? Which means that we've only used one of those edges in our path, vn minus 1 to vn. And that means there's another edge coming out of vn, but because vn isn't adjacent to any vertices that we haven't visited before, it's going to visit another vertex besides vn minus 1. And that vertex already has to be one that we've already visited. Right? So two things, right? Vn has another edge coming out of it because it has degree at least 2. And because Vn is at the end of our algorithm, it has to be adjacent to vertices that we've already visited besides Vn minus 1. So let's say Vi is the new one that Vn is adjacent to that we've already visited. So let's look at our path and make it into a slightly longer walk. So we walk from V1, V2, all the way to whatever Vi is, right? And then we keep on going, Vi plus 1, all the way until we get to the end, Vn. So now that's our path that we outputted from our algorithm. Now remember also that Vn is adjacent to Vi. So if we take all the vertices away that come before the first Vi, what we're going to end up with is the cycle Vi plus 1, all the way to Vn minus 1 Vn. So we walk from Vi to Vn. And then Vn, we walk back to Vi, and that gives us a cycle in our tree. And of course, a tree cannot have a cycle, and so that's a contradiction. And that means there has to exist a leaf because our assumption was that every vertex had at least degree 2. All right, so now that you've seen a little bit of introduction to trees, go ahead and work on the in-class activities in the file called Introduction to Trees that's included with this video.